Good afternoon, everyone. And before going into details of the collision experiments, I would like to focus a little bit more on the background for collisions and motivation for this type of experiments. Why do we need to do the collision experiments in the laboratory? And first, I will start with notation that now we all feel that more and more people are attracted to go north. We also feel that Arctic conditions will test the limits of the technology, and accidents can be completely avoided, and absolute safety doesn't exist. So can we avoid collisions in future? And the history shows that collisions was occurring and still occurs. Here we can see some examples of the consequences of the collisions between the ships and the ice features. And here you're probably all familiar with the Titanic, and this disaster cost life for almost more than 1,000 people. And less probably known case, it's a passenger vessel which collided with an ice and also had an accident which happens in the Arctic conditions. So can we avoid consequences of the event such as loss of the human life, spreading of pollution or damage of the assets? If you look on the literature, we will find out that majority of the scientific work focus on the ice behavior and consider structure as a rigid and not deforming during collision event. And very few literature who address coupled behavior of ice and the structure. It means both ice and the structure are able to deform during the collision event. So I call it shared energy collisions, and they are understudied presently in the current situation. And if we focus more into the knowledge of the shared energy collisions, I remind you where the ice and the structure is able to deform, we will find that there are models which accounts for the water, ice, and the structure interaction in the same and a single simulation. But then, do we have enough data to validate and to check reliability of our models? We can see that there are some historical data. For example, ship collision database with iceberg. But often this data means missing very important information about the ice properties, the shape of the ice mass, or the environmental conditions during the impact. Also, we have some very few, like I would say very few tests, which was done in 90s, and then recently in 2013, this test also was presented in POAC. But often either the data are confidential or the information presented and published are not enough to validate such sophisticated models that include also water in the simulations. So we need more data. And our objective of our experiments was to build expertise in modeling of shared energy collisions under laboratory conditions. And again, I remind you that we're talking about simultaneous deformation of the ice and the structure in a collision run. And then another objective was to obtain meaningful data for the development and validation and verification of existing and analytical models, and also advance the development of a testing procedure for the full-scale collision scenario. We conducted tests at Aalto Ice Basin, and the chosen collision scenario was an impact of approximately 1 ton ice block onto a steel stiffened panel at velocity of 2 meters per second. Here I will talk a little bit about the experimental setup, and then we throw an ice mass here into the purpose-built structure. It's a moored floater with attached to it stiffened panel. We measure the ice mass and ice strengths. During the impact, we measure strains, accelerations of the floater, towing force. We also recorded some high-speed videos and normal videos from 5 different angles, and also attempted to measure the contact pressures, and I will tell you a little bit more about it at the later stage. Here I would like you to show the video from the experiments. Then let's talk about ice. We manufactured the ice using a mixture of the commercially crushed ice and water. We had 10 plastic containers which was filled with crushed ice, and then later it was flooded with water. Then the ice blocks, the samples were stored at -20 degrees in the cold room. And then resulting ice specimens was cut using a chainsaw to its desired shape, and here is the idealized shape of an ice, and here is a photograph of an ice block. And here is a little bit information about the ice properties. I remind you, this is not model ice. This is a freshwater ice. And the density is presented here, and it's slightly lower than it would be expected for the laboratory grown freshwater ice. It means that ice has a slightly higher porosity than that grown under specially controlled conditions. And then the strength for the grain size we are talking about is also slightly lower than expected for the laboratory grown freshwater ice. And so here are the pictures of the microstructure of our laboratory grown ice, and this is the pictures of the microstructures from the iceberg ice. We can see first two similarities is that in our case and also iceberg ice are both granular type of ice. And also our ice and iceberg ice has approximately same level of porosity. But there are also distinctive differences between. For example, if you look on the iceberg ice, the grains are more irregular in shape and has more degree of interlocking between the grains than our ice. And also in iceberg ice there are some features present like a thermal cracks, healed cracks, which we did not look into details in our ice. However, at the present stage we don't know how these microstructural differences will result in the overall behavior of the ice mass upon the impact. Regarding the test panels, which was attached to the float I showed you earlier, we had a steel plate, and it was stiffened with a flat bar stiffeners and two flat bar frames. And the thickness of the plate and the frames and the stiffeners was varied during the test, and details you can find in the paper. In addition to the throwing test, we conducted drop tests in the air, where we drop an ice mass onto the same stiffened panels. And this was done in order to study effects of the removal of the hydrodynamic aspects of the interaction. Then from the drop test, we could see that if the kinetic energy of the ice mass is relatively low, we would have predominantly crushing behavior. However, if the ice has sufficient kinetic energy, the interaction will result in the splitting dominating failure mode, and ice will shatter. We also obtain deformation of the plate, as you can see here, and this could be compared with the deformations which was registered during the ship voyages in the north. Here is the photograph of the hull damage after the encountering the ice, and we can see that both in the laboratory and in practice we was able to achieve the same type of deformations. They call it sometimes hungry horse look deformations. And then the main research results from these experiments that we was able to see that under laboratory conditions as water, we was able to achieve simultaneous deformation in ice crashing and also deformation in the impacted structure. Here we can see that the ice crashing zones from some of the tests and corresponding plate deformations. The plate deformations could be correlated, could be verified against the existing theories and compared with a measured force. However, these experiments could be considered as a pilot test for the future studies. For example, ice specimen preparation should be addressed. For example, to avoid formation of the crack when we're talking about freezing of the large volumes of water, a bottom-up freezing approach is preferred. But in this case, we have to increase significantly the time which is allowed for freezing, as it was in our tests. And also, the better techniques of recording the ice shapes should be done. In our case, we took the pictures from different angles through the plexiglass sheet with a grid on it. However, in future, a more systematic approach to record the ice shape should be addressed. And also the way to systematically shape to a preferred shape needs to be studied. In addition, we found that controlling direction of the impact was difficult in the water. Most of our impact was eccentric in nature rather than direct impact. And then feasibility of the test in water versus the direct testing in air should be considered in the future. In addition, it should be enough sufficient, the ice mass should have enough sufficient energy in order to create deformations in the structure. And for that, maybe quasi-static tests versus dynamic tests should be also considered in future. In addition, we found out that using the pressure sensors that there is uncertainties related to the calibration of this equipment when we're talking about measuring contact pressures from ice. And then we recommend to perform simultaneous measurements of the ice pressures and loads for the single run. And also the amount of the crushing ice which is crushed, it's preferably to be recorded, which could be easily done in the air. In water it's a little bit more challenging. And in the air it could be done by measuring the ice mass before and after the impact. And overall, we recommend that the experimental procedure be repeated with some modifications to improve accuracy of the experimental result. And at the end, I would like to thank Rudiger and his team for help during the experiments, Hydrol project, Aalto University, Research Council of Norway, SAMHOT and SAMHOT partners for participating in this test. Without you, this test won't be possible. Thank you for your attention.
Thank you very much. Right, do we have any questions? Yes?
Well, I'm back again. You are aware that the Russian tanker Norvik was holed in Temur last year in September. There was a hole in a diesel tanker.
Yes, I was aware of it,
yeah.
And nobody could help him because they was busy with something else.
Yeah, and so this is quite relevant, of course. The ice you have simulated is either iceberg ice or multi-year ice, isn't it so?
Yeah, it's a freshwater ice.
Yeah, so that's more like multi-year ice or...
Yeah.
Okay. The multi-year ice flows, they normally have a different shape. They have what they call an ice foot, like a shoe, so kicking in slightly under the water line. So you had more like a rounded ice flow.
Yeah, but the idea was to provide and to get into the concept of the stage of the experiment where you have a shared energy collision. So that's the focus was first of the experiment.
Good. And you also aware that any facilities, if it's on the region shelf, so you'll be able to withstand impact with a supply vessel of 5,000 ton and 2 meters per second. So so maybe we should increase the weight to 5,000 ton and simulate that. So it's similar to the collision with a supply vessel.
We could also consider the normal, regular vessels. In the rules currently, the accidental limit state, which is addressed for the source structures, is not directly addressed. It's indirectly implemented into the formulations with empirical coefficients in it. So it's little bit a debatable questions. What do we talk? Do we talk of the designing of the source structures, or do we talk about the designing of the ships?
I'm talking about designing of the ship, and will have an impact with the supply vessel.
Okay, the floating vessel impact with the,
Yeah. That's interesting.
Thank you very much. Do we have any other questions? Then I would actually address a comment, and some of these parameters like the mass and the speed were also upper safety limit values, because in order to not endanger the people that are working in the facility. All right, so I think that's it for you, Ekaterina. Thank you very much again.